Hello everyone, welcome back to the free lecture series on aerodynamics organized by LearnCAX. Fluid forces. This is the third video lecture of this course. In the previous lecture, we saw different types of forces and how they affect the motion of solids. In this lecture, we will focus only on those forces that are generated as a result of fluid-solid interaction. This will help us understand the resistance offered by the fluid, especially when a solid object tries to move through it, or what it takes to move a solid through a fluid. Here is the outline of this lecture. As I already said, the whole idea of this lecture is to know about different types of forces exerted by a fluid when it flows around a solid object, or to know the amount of force necessary to move a solid through a fluid. To explain why these forces are generated, I have to make use of Bernoulli's principle, one of the very important principles that plays a vital role in the world of aerodynamics. Also, we may have to refresh some of the topics from basic fluid mechanics like viscosity, no-slip condition, boundary layer, and the flow separation. All these concepts will not be covered in depth, but to a certain level sufficient enough to understand the forces generated as a result of fluid-solid interaction. Before we close this session, we will try to do a force balance on an object moving in air. This will help us to predict the net force acting on the object and the direction in which the object will accelerate. And finally, we will apply all our learning on a real-life example of a football or baseball spinning in air, which will explain about Magnus Effect. Please note, here we are restricting the discussion to pressure and viscous forces. Force due to buoyancy will not be covered in this lecture. Let us start our discussion with forces involved in a fluid-solid interaction. A solid interacting with a fluid is subjected to two types of forces, pressure force and viscous force. First, we will look at the pressure force. When two solid objects interact in a process, forces are applied at the points of contact of the two solids. But when a solid object interacts with a fluid, the point of contact is every point on the surface of the body. The fluid can flow around the body and maintain physical contact at all points. The application of forces between a solid body and a fluid occurs at every point on the surface of the body. And this application of force occurs through fluid pressure. The force due to fluid pressure is the one felt on your face when air is blown at high speed, or the one experienced by the protesters or the pirate boat when attacked by water cannons. The amount of force varies with the density of the fluid, the speed with which it hits the solid object, etc. It is the force with which the moving fluid particles hit a solid surface. Pressure always acts perpendicular to the surface of an object. To get the net force on the solid object due to pressure, we have to multiply the pressure times the area around the entire body. Consider a square box or any solid shape immersed in a static fluid. The pressure times the area on one side of the box is balanced by the pressure times the area on the other side because the direction of the pressure force is different. The same is true for the top and the bottom of the box. In fact, for any closed solid shape immersed in any static fluid, the net pressure force acting will be zero. As discussed in the previous lecture, if the net force acting on a body is zero, then the body won't accelerate. That is, it won't change its velocity. In this case, the body will be at rest. This is the case of a static fluid. When the fluid is in motion, the pressure varies around the solid object. and the sum of the forces due to pressure produces a net force. But how does the pressure vary around a body if the fluid is in motion? Well, in a fluid, the local pressure is related to the local velocity. If the velocity changes with location, the pressure changes as well. If the flow is steady and no energy is added to the flow, an approximate relation between pressure and velocity is given by Bernoulli's equation along a streamline. Bernoulli's principle states that the pressure of a moving fluid varies with its speed of motion. If the fluid's velocity increases, a drop in pressure will be seen. That is, an increase in the velocity of a fluid occurs simultaneously with a decrease in the pressure exerted by the fluid. Consider a flow of water down a pipe at a certain rate. In the wide part of the pipe, the flow moves with a certain speed. As the water flows into the constriction or the small diameter portion of the pipe, the area through which the flow moves gets smaller. Because the water doesn't compress, fewer water molecules pass through the gap at a single time. This means that the rate at which the water flows through must increase. That is, the velocity of the water must increase, accompanied by a pressure reduction. The situation is same for an external flow also. When a moving air encounters an obstacle, let's say a vehicle, the fluid path narrows as it flows around the vehicle. Due to conservation of mass, the amount of air moving past any point at any given moment with the airflow should be the same. For this to happen, the air must either compress or speed up where its flow narrows. But at least at relatively low speeds, when you squeeze a stream of air, two things happen. The air speeds up, and as it speeds up, its pressure, that is, the force of the air pressing against the surface of the vehicle, goes down. When the air slows back down, its pressure goes up. We got the reason for the velocity increase. But why does the air pressure go down? For a stream of air to speed up, some of the energy from the random motion of the air molecules must be converted into the energy of forward stream flow. The random motion of air molecules is what causes air pressure. So, transferring energy from the random motion to the stream flow results in lower air pressure. We can find number of examples illustrating Bernoulli's principle over the textbooks and on the internet. Some of them are shown here. But how is Bernoulli's principle being applied or referred in aerodynamics? Imagine a paddler sitting on the bow side of a boat or a canoe on a calm lake water with only a paddle on his right side. As he paddles backwards, an action-reaction force pair is created and the boat starts moving forward. Let us assume the paddler uses some special stroke or technique to counteract the natural tendency of the canoe to steer away from the paddling side. By repeating this stroke continuously, the canoe is expected to move in a straight line. But in reality, the path of the canoe won't remain straight and it might look something like this. What is pushing the canoe towards one side? Because the paddling is done on only one side of the canoe, the water moves faster on the paddling side and there won't be any considerable water movement on the other side. Based on Bernoulli's principle, an uneven pressure is created on the sides with a lower pressure on the paddling side where the water is in motion. So, the canoe is pushed towards the right side. A similar upward force can be generated on an aircraft wing too. This is possible if we somehow manage the air flowing above the wing to flow faster than at the bottom of the wing. But is the upward force generated due to the uneven pressure sufficient enough to lift the aircraft against the gravity? This is always a point of argument. We will discuss on this and much more on flight of an aircraft in further lectures. Now we will move on to the viscous friction force. When two solid bodies in contact, move relative to each other, a friction force develops at the contact surface in the direction opposite to motion. For example, when we try to move a book on the table or floor in one direction, we experience a friction force acting on the book in the opposing direction. And to make the book move, we need to apply a force that is large enough to overcome the friction force. The magnitude of the force needed to move the book depends on the friction coefficient between the book's bottom surface and the floor. The situation is similar when a fluid moves relative to a solid. When a solid moves in a fluid, it experiences some resistance force acting on the body in a direction opposite to the motion. The magnitude of force required to overcome this resistance depends on the property of that fluid, named viscosity. Let me explain. Moving in air is much easier than moving in water. Moving in oil or honey would be even more difficult. Each fluid offers different levels of resistance to motion. It looks like there is a fluid property that represents this internal resistance of fluid to motion. This property of fluid is called viscosity. Consider a stick dipped in a beaker of honey and a spoon immersed in a glass of water. Try to take out the immersed objects from the fluid. You will feel both fluids offer different levels of resistance. It will be easier to take the spoon out of water than to take the stick out of honey. Try doing the same with your fingers. Similar phenomena will be observed. Also, you will feel honey is stickier compared to water. Fluids not only resist the relative motion of immersed objects, but also resist the motion of fluid layers with differing velocities within them. When both honey and water are made to flow over a surface, you will notice that water flows down rapidly, while honey takes more time to cover the same distance. All these discussions talk on the effect of viscosity. But what causes viscosity, or what makes these fluids to behave viscous? And why it differs from one fluid to another? To answer this, we need to go into molecular level of a substance. Any substance is made up of molecules, and based on the strength of attractive forces between the molecules, they are referred to as solids, liquids, and gases. Intermolecular bonds are strongest in solids and weakest in gases. In liquids, the intermolecular forces are weaker relative to solids, but still strong compared with gas. But how do these intermolecular forces cause the fluids, that is liquids and gases, to behave viscous? Let us see what happens when a fluid flows over a flat plate. Here, the blue colored spheres represent the layers of fluid, and the grey colored portion represents the solid flat plate. This animation indicates that the fluid in motion comes to a complete stop at the surface of the plate and assumes a zero velocity relative to the plate's surface. That is, a fluid in direct contact with a solid or the layer of fluid molecules immediately next to the solid surface sticks to the surface and doesn't slip on the solid surface. This behavior of fluid is often called as no-slip condition. The fluid layer that sticks to the surface slows the adjacent fluid layer because of the intermolecular forces between the fluid molecules, which slows the next layer and so on. As a consequence of no-slip condition, a velocity profile is developed and the point of contact will have zero velocity values with respect to the surface. The situation is the same even when a plate moves through a stationary fluid, except that the fluid in direct contact with the plate sticks to it and travels with the plate. In both these cases, the fluid layers are made to move relative to one another. Viscosity is due to the internal frictional force that develops between different layers of fluids as they are forced to move relative to each other. And it is different for different fluids as their intermolecular forces vary. Because of this viscosity, the moving fluid exerts a shear force on the solid, and in the other case, the solid body has to overcome this opposing shear force to move through the fluid. This not only happens at the start of the plate, but throughout the length of the plate. The flow region adjacent to the wall, in which the viscous effects are significant, is called the boundary layer. The fluid layers inside the boundary layer move relative to each other, generating an internal frictional force between layers of fluid. The thickness of boundary layer varies along the plate. The direction of this viscous or shear force is always tangential to the surface. But what about the magnitude of this force? What are all the factors that decide the amount of force exerted on the solid? Once again, Newton is going to help us in finding the answer. Newton, from his parallel plate experiment, came up with a relation between the shear force and the fluid viscosity. Here is the description of the experimental setup. Consider a fluid layer between two very large parallel plates separated by some distance L. Holding the lower plate fixed, when a constant parallel force F is applied to the upper plate, it moves at a constant speed v. Due to the no-slip condition, the fluid in contact with the upper plate sticks to the plate surface and moves with it at the same speed. The fluid in contact with the lower plate assumes the velocity of that plate, which is 0. In steady laminar flow, the fluid velocity between the plates varies linearly between 0 and v, and thus the velocity profile and the velocity gradient du by dy. From experiments, it was observed that for most fluids, the rate of deformation or the velocity gradient is directly proportional to the shear stress, which is nothing but the shear force F per contact area A. Fluids for which the rate of deformation or the velocity gradient is linearly proportional to the shear stress are called Newtonian fluids. In one-dimensional shear flow, shear stress can be expressed as, where the constant of proportionality mu is the viscosity of the fluid. Slope of this velocity profile is dy by du. The velocity gradient can also be expressed as the inverse of the slope. So the expression for shear stress can be modified as, this shows the shear force required to move a solid object through a fluid is directly proportional to the fluid's viscosity and inversely proportional to the slope of the velocity profile at that point. So, for the same fluid and velocity, the amount of shear force can vary based on the velocity profile. Along the plate length, the boundary layer thickness increases and the slope is also increased. This explains why the amount of shear force varied along the length of the plate. To summarize, the shear force exerted by the fluid on the solid surface depends on the fluid viscosity, contact area between the fluid and the solid, and the slope of velocity profile, which in fact depends on the free stream velocity of the fluid, the solid velocity, and the thickness of the boundary layer. This clearly indicates the shear force does not depend on the material of the solid object, but the surface roughness does affect the amount of shear force. Although this is not visible in the formula, the surface roughness affects the boundary layer profile. For a flat plate with smooth surface at the top and rough surface at the bottom, The boundary layer or velocity profile at same locations from the leading edge are shown here. For the side with smooth surface, the boundary layer remains laminar. But for the side with rough surface, the boundary layer becomes turbulent. Yes, a boundary layer may be either laminar or turbulent depending on the value of the Reynolds number, which is a ratio of inertial forces to the viscous forces. For lower Reynolds numbers, the boundary layer is laminar, and for higher Reynolds numbers, the boundary layer is turbulent. But even at low Reynolds numbers, a small disturbance or roughness on the surface can make the boundary layer turbulent. A turbulent boundary layer has a steep gradient of velocity at the wall and therefore exerts a larger shear stress compared to that of a laminar one. So we can conclude the surface roughness increases the amount of shear force exerted by the fluid on the solid object trying to move through it. But if we say air applies more shear force on the solids with more roughness, then why do golf balls have dimples on them? Why don't we have a smoother ball to play? Why to introduce disturbance on the surface, which according to our learning will bring more opposing viscous or shear force? I guess something unfair is happening with the golf balls. Maybe we are concluding on the surface roughness issue very soon. So we will wait till the discussion on flow separation and then revisit this dimple problem. When a fluid is forced to flow over a curved surface at high velocities, the fluid follows the front portion of the curved surface without any problem, but it has greater difficulty remaining attached to the surface on the back side. At sufficiently high velocities, the fluid stream detaches itself from the surface of the body. This is called flow separation. The effects of flow separation are felt far downstream in the form of reduced velocity compared to the upstream velocity. This region of flow trailing the body is called the wake. How does this flow separation affect the motion of a solid body? Flow separation forms a low pressure region at the backside between the body and the fluid stream. These low pressure regions behind the body where recirculation and backflows occur are called the separated region. So, with a high pressure region at the front and a low pressure separated region generated due to flow separation at the back, the solid body will face more resistance to move. It is usually difficult to predict the location of flow separation unless there are sharp or abrupt changes in the shape of the solid surface. The location of the separation point depends on several factors such as the Reynolds number, shape and orientation of the body, the surface roughness, and the free stream velocity fluctuations. Yes, you heard it correct. The surface roughness affects the location of flow separation. In fact, it delays the flow separation and thus reduces the low pressure region behind the body. Let us see how the surface roughness manages to delay the flow separation. The surface roughness makes the boundary layer turbulent. In a laminar boundary layer, any exchange of mass or momentum takes place only between adjacent layers on a microscopic scale, which is not visible to the eye. A turbulent boundary layer, on the other hand, is marked by mixing across several layers of it. Packets of fluid may be seen moving across. Thus, there is an exchange of mass, momentum, and energy on a much bigger scale compared to a laminar boundary layer. As a consequence of intense mixing, a turbulent boundary layer has a steep gradient of velocity at the wall and therefore a large shear stress. But it doesn't let the flow separate from the surface easily. So, in case of turbulent boundary layer, the flow separation is delayed when compared to a laminar boundary layer. Now we got the reason why golf balls have dimples on them. Although surface roughness increases the shear forces on the ball, it reduces the net pressure force acting against the ball motion. So it's a trade-off between the viscous and pressure forces acting against the ball's motion. We compromise on the shear force but save lots of energy by avoiding or delaying flow separation. At times, the effects of flow separation can be dangerous too. An important consequence of flow separation is the formation and shedding of circulating fluid structures called vortices in the wake region. Periodic generation of these vortices downstream is referred as vortex shedding. The vibrations generated by vortices near the body may cause the body to resonate to dangerous levels if the frequency of the vortices is close to the natural frequency of the body. This situation must be avoided in the design of equipment that is subject to high velocity fluid flow, such as the aircraft wing and suspended bridges during heavy winds. Having discussed about the forces exerted by the fluid on the solid, let's try to do a force balance on a body moving in air, or let's draw a free body diagram. Free body diagrams are diagrams used to show the relative magnitude and direction of all forces acting upon an object in a given situation. This will help us to find the net force acting on a body moving in air. Let's watch in detail. What happens to a body moving in air? Only the air particles in the immediate vicinity of the surface are acting on it by applying some forces. On each point of the surface, the adjacent air particles apply a perpendicular force due to pressure and a tangential force due to viscous friction. Drag force is nothing but the net force acting against the direction of body motion. In order to evaluate the net force acting against the direction of motion, the algebraic sum of all the components of pressure and viscous forces along the direction of body motion are to be considered. This will give us the drag force. Simple, isn't it? Yes, the terms drag and lift forces are nothing but the components of pressure and viscous friction forces in different directions. We will have a detailed discussion on drag and lift forces in the next lecture. From now on, I will start using the term drag. The friction forces always have the effect of opposing the body motion. But the pressure forces behave differently. It always acts perpendicularly to the surface. In proximity of the front part or the leading side, it has a component oriented in the direction against the body motion. At the maximum body thickness, this component is 0. In proximity of the body's trailing side, it is oriented in the direction of the body motion. Thus, from the leading edge to the maximum thickness, the effect of the pressure is opposing the motion, and from the maximum thickness to the trailing edge, the effect of the pressure are helping the motion. The algebraic sum of all these components is the portion of drag due to the pressure. In case of a sudden or abrupt change in the shape of the body, past the maximum thickness, the flow separates and a wake region is formed. The pressure in the wake region is much lower than that in the same region without the wake. This results in increased net force acting against the body motion. It is now easy to understand that, depending on the shape of the object and of the flow condition, the part of the drag due to the pressure can be lower or greater than that due to viscous friction. Let us see in detail what happens to an object spinning in airflow. The simplest case to consider is air flowing around a football. In case of an ideal fluid, the free body diagram will look something like this. Here, the velocity of air at point A and point B are the same. So, according to Bernoulli's principle, the pressure would have same values at points A and B. Let us kick the football and give a clockwise speed to it in a real fluid. Let us see what happens at point A. The speed of circulatory motion adds up to the basic flow and we obtain a net increment in airspeed. An opposite situation happens at point B. The speed of circulatory motion is directed in the opposite direction and it is subtracted to the basic flow, resulting in reduction of airspeed. As expected from Bernoulli's principle, the pressure at point B is higher than at point A. This produces an upward force on the football. This generation of force due to circulation is called Magnus Effect. Magnus effect can be seen in football, baseball, and many other cases. This effect also helps us to understand the lift generated on an airfoil. We will discuss this in the next lecture. Now we have learnt how to use free body diagram of forces and predict the net force acting on a solid body. Thanks for listening, and if you have any feedback or queries, you can mail us at info@learncax.com. See you around for the next lecture on aerodynamic forces, lift and drag.